Okay, so the first one is going back to last unit, and we've got shipment of pumpkins, mean of 14.5 pounds, standard deviation 2.7. What weight pumpkin represents the 80th percentile of the distribution? So this is a inverse norm problem, because you can see right here that it's the percentile is given. So of course, remember something like this, you're going to have your z-score, x minus mu divided by the standard deviation. In this case, I don't know what that x value is. Actually, I'm going to do this. Well, anyways, I'll just do it right here. The mean is 14.5, and the standard deviation is 2.7. So basically, I need to figure out what the z-score is. My calculator tells me that. You just do inverse norm, and you plug in 0.8 for your area, and that shows 0.8416, so 0.8416 equals x minus 14.5 over 2.7, and let your calculator do all those calculations for you, and you can get your final answer of what half of you got right here, 16.8. All right, so if you mixed up your numbers in any way, shape, or form, you might have gotten one of these other answers. But there you go. It should have been 16.8. Okay, the second one right here. At a particular ranch, horses weigh an average of 1,138 pounds, standard deviation 115. They eat 18 pounds of hay on average with 2.2 standard deviation. 8.87 correlation between a horse's weight and how much it eats. How many extra pounds of hay does a horse require each day for every additional pound that it weighs? So this definitely goes back to what we were talking about yesterday. And if you weren't sure, but after that first question, you see this 0.87 correlation. You can hopefully see that we're dealing with two quantitative variables, the weight of a horse and the weight, how much hay they eat. So there's two different quantitative variables. So we're dealing with scatter plots, correlation, all that fun stuff. So now we just need to interpret the question. How many extra pounds of hay does a horse require each day for every additional pound that it weighs? Well, that's just a different way of talking about the slope of the line. So for every additional pound, we're going to have to feed it some extra hay based on, on average. So how much extra hay per pound? So this is where we just need to figure out the slope. And the slope, I'm not sure if this equation is on the AP formula sheet. So what you're going to want to do is write this one down, have it in your notes, have it available, kind of find some place you can access this. So it's the correlation times the standard deviation of y over the standard deviation of x. That's supposed to be a y up on top. So luckily, that's the only thing that we need to worry about. It looks like there's a lot of data in here, a lot of things to worry about, but it's actually a pretty straightforward problem. I can take the correlation and plug that in. I can take the standard deviation of y and standard deviation of x. So that's going to be a little tricky. So how many extra pounds of hay does a horse require each day for every additional pound that it weighs? We need to kind of think through what that means as far as explanatory and response variables go, and which one's your y and which one's your x. So it looks like the weight of the horse will explain the amount of hay that they eat. So if I'm thinking of this as a scatter plot, weight will go down here and hay would be right here. So it looks like my y is going to be hay, which has a standard deviation of 2.2, and that means the x is my weight of the horse, which is 115 standard deviation. And remember, doing this calculation on the right with the standard deviations allows us to scale the slope for our particular scatter plot. So when you plug that in the calculator, 0.87 times 2.2, and then you divide that by 115, you should get this answer right here. So hopefully all of you who are able to get through this problem, that matches up with what you found. Okay, when I was making this bell work, I forgot it was a short class, so you might not have had, I'm kind of rushing through it a little. Okay. So today we are looking at some conceptual stuff, especially when we get down here to the standard deviation of the residual and the coefficient of determination, R squared. This is going to be some heavy conceptual stuff going on, but when we get down to the end, I don't show it. We're going to get a little bit of practice, and hopefully that kind of, you know, wraps it up and helps it make it a little clearer. Remember, Friday, we're going to spend the day just kind of going over and making sure all the stuff is really well understood. So we're going to start by looking at the calculator. Yesterday we did a problem in class, and so I'm picking that same one intentionally because hopefully you still have those lists on your calculator from yesterday. You can just double check to make sure you have this data still in your calculator. If not, you can come back to this later, but I'm not going to take the time now to have you enter it. If you want to create the regression line and actually see it, first of all, you know how to make a scatter plot of this data. And what that means, I'm just bringing all this up. So you could go and you could look at the scatter plot, and we're going to make it so you can see a regression line running through it. Every time you run a linear regression, the calculator stores that regression line equation. And to access it, it's a little bit weird, but what you need to do is you would go to your y equal, well, first of all, to actually create the line, you want to go on your calculator to y equals. So you're probably familiar with this from Algebra 2 or other classes that you've taken. And for any of those functions, you can, while you're just hovering on one, just hit variables, vars, and in there you'll have the option of statistics, number 5. And then once you're in statistics, you'll need to scroll with the arrows to the right until you get to equations, EQ. And the very first one is your regression equation. So all you have to do is select that, hit enter, and you're going to see a really weird linear equation fill that function, and that is your regression equation. So now, if you have the scatter plot turned on and you have this function, you can just do zoom 9, and not only will you see the scatter plot of the data, but you're going to see the regression line running through it. Okay, so hopefully you're seeing that. And this is really mostly useful if you're asked to create a scatter plot and you wanted to see what that looks like on the calculator to make sure it matches up when you draw it on paper. And if you want to see the regression line running through it, you can actually show that on the calculator. That's not your final answer, of course. People can't just see your calculator, but that'll help you know, like, okay, it moves through here, and so when I draw it on my paper, that looks approximately correct. But you know, it could be a useful thing to know. Okay, now a lot of times with AP questions, they're not going to have you take your time to plug stuff into lists, create the regression equation, all that fun stuff. They're just going to ask more either conceptual questions or ones where they have you do some calculations. Anyways, enough on that. If you need to refer back to that, of course, it's in the presentation from today. So a residual plot is just what it sounds like. Okay, so the residual of every data point is plotted against its x value, generally. Now, this is a side note, but I think it's worth knowing. In more advanced statistics that use multiple regression, you wouldn't plot it. Notice right here, the x we're measuring is measured tree height, and here it's measured tree height. You can do a residual plot where you do it against the predicted value. And there's reasons for that. We won't get into it. But when you get into multiple regression, you wouldn't necessarily use the x. But let's not worry about that. For now, we will use the x. And you can see this is almost like flattening this line. So almost like you took this regression equation and made that line perfectly flat. And notice that all these points kind of correspond. You've got this very first point down low. Well, here's the residual for it right there. you've got this point right here, which looks to be not an outlier, but it's certainly got a big residual. So you can find that one right here. And then this one with maybe one of the biggest, maybe the biggest negative residual right here is going to be represented right here. So they just took the same basic scatter plot form and just flattened it out. So it doesn't look much different, but it can reveal some really important things that might not be visible from the data originally. Okay, and we'll talk about that. One thing that it could show us, and sometimes it's really obvious from the main scatter plot, but sometimes the residual shows this better, is it could show us whether or not we have equal variance along the entire thing. So what is ideal is to have a situation like this. We want it to look like kind of a no correlation scatter plot where you have a lot of equal variance of your residuals along the entire length. But you could have a situation where, you know, it gets less and less or more and more as you go along. Now keep in mind what a residual, what a regression line is for. It's supposed to model the data. If it's pretty constant throughout, then that's going to tell us, it's going to help us have faith in the predictive value of this. Because we know, yeah, it's not going to be perfect, but anywhere along the line is basically the same error along the way. And we'll talk about the residual standard deviation, but we have pretty good confidence in this model. Here, at the low end, it's not very predictive. Notice at this end, it's pretty good. Whatever we predicted right here isn't going to be too far off, but down at the low end, wow, there's a lot of uncertainty. And then vice versa on this one, at the high end, wow, there's a lot of uncertainty when we get over here compared to at the low end. So that makes it less reliable as a model. And, you know, we just need to be careful of that. So when you see a situation like this, a linear regression might not be appropriate. Okay. So if there's a conceptual question, you just might say something to the effect, a linear regression might not be appropriate because it doesn't show constant variance the entire length. All right. That's nothing too bad with that idea. Residuals and residual plots. Now, moving on to a different idea, and this is one that's a little more common perhaps. Well, I don't know if it's more common, but what we are hoping to avoid, like we saw before, is kind of like a random scatter plot with no correlation. So this is pretty good. I don't see any pattern, but if we do see a pattern, like right here in this second one, there's definitely a nonlinear pattern in our residuals. So that would tell us that it's not appropriate to use a linear regression for a nonlinear data set. So I'm going to get rid of a couple things here. And this is most useful for situations where you have data which appears to be like almost a perfect correlation is linear. So you got this regression line and it looks like, oh my gosh, it's perfect. But then you look at the scatter or the residual plot of that, and you might see, so if here's the residuals, you know, there's a trend, and hopefully you can see all the dots like this. And you might not see the dots very clearly, but hopefully you can see them well enough, where there is this very subtle but obvious nonlinear pattern. And you can't see it from the main scatter plot. In the residuals, it shows up very clearly. So it's one of these like a very subtle nonlinear pattern going on. So anyways, if you see it, just say it's nonlinear. We shouldn't use linear regression, you know, therefore, and anyways, these are kind of the primary tool. The residual plots are primary tools for determining the appropriateness of linear regression. So that's one thing a residual plot is, or that is the main purpose, but we have some, well, actually, before I talk about that other stuff, let's do a little bit of practice right here. So just, you got 3 residual plots. This one on the left, someone comment about what you see there.
It has like a slight dip in the middle.
Yep. So is this showing a pattern in the data, or not? Or let me just ask this question, because the actual question is, what about the appropriateness of a linear model? Would you say it's appropriate to use a linear model for this one or not?
No.
No. Okay. Yeah, and I would say there's enough of a trend right here that's nonlinear. We shouldn't use it. And this might not be caught from the scatter plot, but in the residual it shows up. Okay. In the second one, is a linear model appropriate for this?
No.
Okay, we could say no. We might, because it's not that constant variance, we might say something like it might not be appropriate, because it just kind of depends on other factors, you know, but it's not, certainly it's not going to be the best kind of linear regression that we're going to ever get. So it might not be appropriate here. This last one, is that one good?
Yes.
Okay. So yeah, nothing like that's going to stretch your mind too much here. Hopefully this is all very straightforward. But yeah, you can see it's got no real pattern. We've got equal variance on both sides. So it looks good. That's a good residual plot. Okay, so if you want to create a residual plot, this is, I mean, there's a number of steps here, but it's actually not that bad. You might have earlier just run a the linear regression for that first data set. So if you wanted to see a residual plot of that, that's not too hard to do. So all you need to do, anytime you run a regression analysis, the calculator automatically saves the residuals. So this is all going on in the background. And to create the residual plot, you're going to create a scatter plot for your X list. You're going to keep that the same. So whatever you had as your X list for your original scatter plot, keep that X list the same. But for your Y list, you're going to have to search for the residuals. What you will do is you will go down to Y list. And when you get there, you have to hit second and stat, which pulls up the list. And you can see list written in blue above that. And as soon as you get to all the lists, of course, you can see list 1 through 6, but down at the bottom, number 7 is residuals. And just select that as your Y list. And when you show that scatter plot, you might want to turn off the Y equals on this, but it doesn't really matter. But if you do zoom stat at this point, it's going to show you a residual list for that data set. And you'll see that line running through the middle, that's actually just your x-axis showing 0. So anything above the x-axis is going to be a positive residual. Anything below the x-axis is a negative residual. Okay, again, this is just something that if you want to get a visual on the residual plot, this is one option. But a lot of times it's provided for you. Okay, I'm not going to spend too much time on this. If you have questions on calculator stuff, we can clarify that later. But again, the instructions are right here. So now we're gonna, so that's all dealing with residual plots. And now we're gonna talk about this particular concept, residual standard deviation. They call it S sub E. I think E for error. I don't know if that's exactly what it comes from, but S sub E is your residual standard deviation. Okay. And just like any other set of data, residuals can be plotted in a histogram and the standard deviation can be found. And the histograms for both of these, so I have a couple examples here. Scatter plot, regression line running through, here's the residual plot. But then when these are put into a histogram, you can see it's approximately normal here, or approximately normal here, maybe some outliers. And one thing, I think I talked about that right here. We can identify outliers here, but let's not go overboard on this right now. Any point, this is a concept that I forgot to mention when we were in the last unit, which it didn't come back to bite you in any way, but sometimes when you're looking at histograms, outliers are anything that's more than 2 standard deviations from the mean. Okay, so if you have a z-score of 2.5, that might be considered an outlier. So in this case, if we found the standard deviation of the error, we could figure out which of these are outliers and stuff like that. And that might be important to know to determine if the linear model needs to be changed, for outliers affecting it. Okay, but like I said, I don't want to go overboard with this idea. I've never seen an AP problem where it gives you a scatter plot and then asks you to go through, create a histogram of the residuals and determine outliers from there. But as a brief aside, and I hope I'm not getting too far into the weeds or too much stuff right now, but question 6 on the FRQs on your AP test is what's called an investigative task. And an investigative task is one where it assumes you have a certain level of background knowledge about statistics. And it might give you a novel situation, one that you've never seen before. And it doesn't use exactly formulas and calculations that you've used in the past, but it gives you some background, it gives you some information to set you up, gives you a little bit of explanation. So a question like this would be appropriate for an investigative task. Like, here's a scatter plot, create a residual plot, and might talk about the standard deviation of the errors and stuff like that. Again, don't worry about that too much. It's just a little bit of side note. So anyways, standard deviation of the residuals. Let's get back on track with that. Okay, so one of the uses of the standard deviation of the residuals is to assess the strength of the model. Okay, and this, to start off with, the standard deviation of the residuals is the average distance that an actual y value is away from the regression line. So if you have a bunch of residuals, here's a residual plot. If you have a bunch of residuals, I know these dots don't show up very well, then your standard deviation is going to be the average distance that it is away. Maybe this is your standard deviation. And it can be plus or minus. So it's the same thing like we did with before with our histograms. So generally speaking, the smaller a standard deviation of residuals is in comparison to the standard deviation of the y values, the stronger the model. Okay, so maybe the best way of talking about this, and this should be subscript right here for the y, your standard deviation of y shows the spread of all of the actual y values, while the standard deviation of your residuals, again subscript here, shows only the spread of the residuals around the model. So if your standard deviation of the residuals is significantly smaller than the standard deviation of y, that means there's less variability in the points around the model than there is from the scatter plot. And I want to give an example of this. Imagine you have a data set which looks like very low or no correlation. And let's say you've got some regression line, okay? The variation in your y looks like that. If I created a residual plot of this, it's still going to be like really scattered. There's going to be a lot of variation here. So notice, just comparing the variation in the residual plot here to the variation in the original data here, the variation is pretty much the same. So this is not a very powerful model. So let's compare that to one with a high correlation. So notice the variation in y is still quite big. But when I show the residual plot, all my residuals are going to hover right around the line, and I've got very little variation in those residuals. So if I compare the residuals in this one now to this, the fact that my standard deviation for the residuals is so much smaller than for the Y values, that shows me this is a very powerful model, okay? And that's useful if all they give you are these two numbers. Then you can conceptually say, oh, this is a pretty strong model. So hopefully that visually is making sense. Okay, and that's just kind of summarizing it again. Again, I forgot the subscript here, but you get the idea. So that's one use of the standard deviation. So this was a problem in your book. It's not one that I asked you to do, and I'm not going to ask you to plug this data in. It's going to take a while. But we are correlating weight in pounds and trying to predict body fat percent just from someone's weight. So when you run the numbers here, if you plug this in, you would get a standard deviation in your Y values, body fat, of 9.563. The standard deviation of your residuals is 7.049. So just comparing those two numbers, you know, this is only 36% bigger than this one. So I guess you could say it's a factor of 1.36. This is not super powerful, and we're going to look at another measure of this in just a second. But, you know, I don't have a numerical value to say, oh, this is the ratio you should be looking for to show that it's a powerful model. Why does this happen every time? Okay, but I do have, but it is just kind of, if you had a comparison of two different values. So someone asked earlier, how would you know if this was powerful? Well, let's say that the standard deviation of the residuals wasn't 7.05. Let's say it was 1.13. I'll just give it something that looks more official. So now, if that was 1.13, we'll now compare that 9.563 to 1.13, and that's, you know, approximately 8 times bigger. So that difference between the two, and the ratio between it, you know, that shows that this is a pretty big difference. That's probably going to be a pretty powerful model. Okay. Again, I wanted to present kind of a conceptual understanding of the standard deviation, but I'm not sure that you're ever going to have to deal with this like on a very complex level with calculations. Okay, so more commonly, and this is more common because it goes along with correlation. So it's really easy to find this number. The coefficient of determination is another way of assessing the power of your model. Okay, and it's just straightforward, the square of your correlation coefficient. So the correlation, I said, is always a decimal, but R squared is usually presented as a percent. So keep in mind that since your correlation is going to be between -1 and 1, when you square any number, it's never going to exceed 100%. And so let's talk about, what does this percent mean? And basically, R squared tells us what percent of the variation in the Y values is explained by the model. So, and we'll get into that a little more. Since the correlation is less than 1, R squared will always be less than the correlation. And here's an example to make sure that's really clear. So if you had a correlation of 0.7, that means 49% of the variation in Y is explained by the model, because 0.7 squared is 0.49. So your R squared is going to be always less than your correlation. Okay. And another way of thinking about it is that it tells us how successful our model is at explaining the variation in the response variable. And this, again, is your Y. Okay. So not last note, but another note here. Simply having a high R squared does not mean that a linear model is appropriate. I showed an example of something that looks linear from a scatter plot, and you find out it's nonlinear. So if you determine that something is nonlinear from the picture or from the residual plot, then it doesn't matter what R and R squared you have, it's not appropriate to use that. So nonlinear automatically disqualifies using any of this information. Keep that in mind. Okay, so going back to this example, Again, I'm not asking you to plug the data in, but if you ran a linear regression between weight and body fat percent, you end up with an R-squared value of 48.5%. So in context, this means only 48.5% of the variability in body fat percent is explained by the regression model we calculated. Now, I say only 48.5%. That might be a really good result, you know? Depends on what your standards are. The other 51.5% of the variability must be from other factors. So if we know that weight accounts for 48.5% of determining what your body fat percent is, well, there could be all kinds of things like, genetics, how much you work out, how much of that weight is muscle versus just fat, all kinds of factors going in. Okay, so now that we've kind of run through this conceptually, the name coefficient of determination makes a little bit more sense. And I'll just go back to that last example real quick. So what we've determined is 48.5% of the variability in Y is explained by the model. So we've determined that, or rather the model determines 48.5% of our change. So the rest of it, anyways, we already talked about that, what the rest of it means. So this is one last thing that I just need to throw in here, but it's one of the most important ideas. If you are only given R-squared to ask what and you're asked what the correlation is, you have to be careful. So R-squared is always going to be positive. If you have a negative correlation and you find R-squared, it's going to be a positive R-squared. So if all you have is R-squared, you need to consider if the correlation should be positive or negative. So let's consider this one. The R-squared for amount of exercise versus weight is 38.4%. What is the correlation of these two variables? So, I mean, it's easy enough just to take your 0.384 and take the square root of it, because R-squared is 38.4%. So I'll just run that math real quick. 0.384. That gives me 0.61, or I'll round it to 3, so 0.620. All right, well, that's all well and good. But now we need to consider if is this a positive or a negative correlation? So I will kind of think of it this way. So presumably, amount of exercise is going to explain someone's weight. So I'll just put exercise down here, weight right here. And conceptually, if someone gets more exercise, what do you think would happen to their weight?
It'll decrease.
Decrease. So this is probably a negative correlation, right? So I don't know how strong it would be. Well, it says 0.62. I made that up. But I could say this is going to be a negative 0.620. So the only clue you're going to get to whether it's positive or negative is your own intuition and looking and thinking in the real world, what direction would that correlation be? So now you might say, oh, more exercise means you're working out more, you get more muscle mass, so maybe you go up. But I think generally we think if you exercise more, you're going to lose weight. So I think it's fair to say a negative one right here. Okay. So the last thing right here is just a very simple overview of our assumptions. And we're going to talk about these more when we do some practice problems in a second. But if we've got regression, we're trying to figure out, was it appropriate to use a linear regression? We need to first of all check, were they both quantitative variables? So, okay, good, yes. Were they the scatter plot? Does it appear to be linear? Yes, and of course, remember along with this, we could check the residual plot if that's available. Equal variance. So if we look at the residual plot, do we see constant variation along the way? If so, we're good. Outliers don't disqualify it, but we would want to report that. Say there is a potential outlier at this point. If you can report the correlation with and without the outlier, that's good. Depending on the question, you might not have access to, do that calculation. But, just keep in mind outliers can throw it off, and we'll talk about that more next chapter. So the last part, what I wanted to do is just run through a couple of problems. And some of this is just a repeat of what we did yesterday, but we'll also kind of incorporate what we did today. So in this one, we've got a correlation. And the first thing it asked me to do is find the linear regression equation for these two variables. So I can see, luckily it gives me a scatter plot, and I've got income as the X and total yearly purchases as the Y value. So income versus total yearly purchases. Income I can see as the X value, total yearly purchases is the Y. And right here it tells me the mean and standard deviation of each of those. The correlation is given right here, 0.722. So because it's this way, I have to do some calculations. I can't just plug the list in and have the calculator do it all for me. But that's okay, we know what to do. We are going to start with our generic correlation equation. And we need to solve for A and B. And I'm going to start by solving for the slope. So my slope, remember the equation and have this in your notes. I already mentioned that, but just a reminder, is going to be the correlation times S sub Y over S sub X. I already determined which one's my X and my Y, so I just need to find the standard deviation. So the correlation, again right here, is 0.722. So now, standard deviation of Y. Well, here's Y, total yearly purchase. So the standard deviation of Y is 253.62. Standard deviation of X is this one right here. So standard deviation of yearly income, 16,952.50 cents. So we've got the numbers. We can just use a calculator to get the answer of the slope. All right, so I just wanted to add the units to this one. I might not do this at the end, but basically $0.0108 in spending for every dollar in income. And that's the slope that we just found. So now I can come over here. And one thing to remember is that one point that always passes through the regression line is Y bar, X bar, or X bar, Y bar. So, so if I just substitute X bar and Y bar into this, and I just found the slope, so I can plug this in to solve for A. Y bar, remember, is the average Y value, which is right here, 572.52. A is unknown, B is 0.0108, and the average income is 50,343.40. So again, basic algebra at this point, so you can calculate that at home and we'll see what the answer is. And that's what I got. So you can determine if you agree with that or not. So just to put this in context, I'm not just going to plug it into this equation right here, which I could, but I want to provide a little bit more context. So I'll just put, you know, purchase, which in our case that'll be like the total annual purchase. The predicted purchase will be $28.81 plus, and then 0.0108. And then of course I have the unit right here. I'll just draw an arrow for it to save time, times not just X, but it's going to be income. So whatever the income is of the person, that's going to be kind of our determining, our explanatory factor. All right. So that's the linear regression model that we're going to use. Okay, the next question. This is just a conceptual one. We would want to write a sentence if this is an FRQ, but do the assumptions and conditions for regression appear to be met? And I just listed 4 of them. I don't expect you to have that memorized just yet, but I'll just run through it real quick. Do we have quantitative variables? Well, income and yearly purchases are both quantitative, so yes. So they're both quantitative. Do we have a linear scatter plot? And it sure looks linear to me, so I think we've met that one. Do we have constant variance, equal variance along the entire length? And it looks like, you know, if we created a scatter plot, that would be pretty constant variance along the way. I feel like that one's met. And lastly, do we have any major outliers? I don't see any. You know, this point right here is a little big, but probably not enough to where I'd call that really an outlier. Okay, so I would say something to the effect, yes, a linear regression is appropriate because we only have quantitative variables. We have a linear form. There's equal variance along the entire regression line, and there are no major outliers. So we've met all conditions. But again, write that out in a sentence. I'm not doing that here to save a little bit of time. Okay. So any questions on this so far? I haven't paused for questions in a while. Okay. Again, if questions do come up, you can raise your hand or just jump in. So the next question, what is the predicted average total yearly purchase for someone with a yearly income of 20,000? We saw something like this yesterday. So really, I'm just going to do the first one. It asked for 20,000, and then it also asked for 80,000. Let's just plug 20,000 in. So if 20,000 is the income, well, 20,000 right here is income. 0.0108 is the slope. 2881 is the oops, sorry. 2881 is that y-intercept. So now I can figure out the predicted value from that. All right, I'm not sure, I just deleted my result accidentally. So that gives you a little bit more time to find it. You're still plugging the numbers in. All right, so what I got was $244.81. And hopefully that's what you got as well. Okay, so there it is. What percent of the variability, if we had 80,000, we'd just do the same thing, but I'm not going to do that one. What percent of the variability in total yearly purchases is accounted for by this model? Okay, so what are they asking us to do right here?
Could you repeat the question?
Oh yeah, we're looking at D. So it says, what percent of the variability in total yearly purchases is accounted for by this model? So what should we do to get that answer?
Do we just square the R?
That's it. Perfect. Good job. So all it's really asking for is R squared. And if it's asking for R squared, there's nothing special to it. We don't have to do anything besides take the R and do the squaring and let's see. It's the easiest calculation that we're going to have to do with this entire thing. So it looks like 50, let me do that. So 52.1% of the variability is accounted for by this model. And we can just use their own language in our response. 52% of the variability in total yearly purchases is accounted for by this model. Okay, and the last one. This is conceptual. Is this regression a useful one for the company? Any thoughts? Awkward wait time, huh? So let me ask. Oh, go ahead.
I think it's useful because 52% of all the data is shown, and then that kind of gives you a feel for what you're trying to know.
Okay, yeah. If we know where 52.1% of the variation in customer spending is, that's actually a pretty good number. It doesn't explain 100%, but you're never going to get that. So that's pretty good to know how to account for all the variation. So this tells you if you could identify the income of your shoppers, then you could, with some level of accuracy, kind of guess at how much they might spend at your store over the course of the year. So I think it is useful. I mean, it's one of these things, you just answer it, make sure you have some good sound reasoning behind your decision. You can see an example answer at the back of the textbook for this. Actually, this is an even, so I don't know if you have that answer, but there are questions like that you can see. Okay, just going through this one, these two should go much faster. And this is all we're looking at today. So we don't need to know these previous exercises, but it says here, for exercise 2's regression model predicting fuel economy from the car's horsepower, the standard deviation of the residuals is 3.287. Explain in context what that means. So remember, your standard deviation of your residuals is the average distance that an actual data point is from the model. So in context here, we could say, well, and let's remember, what's predicting what? It's predicting fuel economy from horsepower. So the fuel economy is what's being predicted. And we could say the fuel economy, or let me start that over again. The actual fuel economy of a car is on average 3.287 miles per gallon different from the model, from the predicted value. All right. So this is just and I might not phrase it exactly the way the book would, but it's showing that there's an understanding. Okay. So hopefully that one's clear enough. That's really all you have to do with that question. Not much more to it. And the last one right here, this goes back to the very last thing we were talking about before we jumped into the practice problems. You were given only an R squared of 12.4%. And we have a regression of duration on duration of a roller coaster on the height of its initial drop. So the phrasing here, we need to figure out which is our X and Y. Duration on the height of its initial drop, which means duration is being predicted from the height. So this is what our scatter plot would look like. Okay, R squared is 12.4%. Let's figure out the correlation. That's what part A is saying. So of course we can do square root of 0.124. So we have 0.352. And the question we need to ask is, should this be a positive or negative correlation? Okay, so think about this, just the drop, I should put right here. Do you think a roller coaster with a higher drop is going to last longer or be a shorter ride?
Longer.
Longer, I agree. So generally, if this goes up, this is going to go up too. So we should have some kind of a correlation that looks like this. And we don't need to look into this any further except to kind of conceptually figure out positive or negative correlation. Well, that's a positive correlation. So R is going to be positive 0.352. Okay, so explain why. Well, you know, we just kind of visually said it. As drop height increases, duration should be longer. What would you predict? This is where, and it's important to kind of go through these. These look really difficult at first. What would you predict about the duration of the ride on a roller coaster whose initial drop was 1 standard deviation below the mean drop? The only information they gave us was R squared. So what the heck do we do with this? And this is where it's helpful to think about our slope equation. So it's R times S sub Y over S sub X, which I'm going to rewrite as R times S sub Y over 1 times S sub X. So that means for every 1 standard deviation in X that we move, we're going to go up or down R times the standard deviation of Y. So in this particular example, I'm going, let's see, 1 standard deviation below the mean. So I'm going to move -1 standard deviations of X, which means I'm going to be going negative R times the standard deviation of Y. Okay, so that means for going 1 standard deviation below the mean in drop should make the duration go down R times the standard deviation of Y in duration. So we would expect a duration R times, well, we know R, so I should put 0.352. So 0.352 times standard deviation of Y below the mean for duration. All right, so is that making sense? Okay, and then likewise for the next one, if it was 3 standard deviations above the mean drop, well, then that would mean, I'll just come over here. If I'm going 3 standard deviations of X above the mean, then I'm going to be 3 times R standard deviations of Y above the mean. So 3 times R is 1.056. So I would expect a duration 1.056 times the standard deviation of y above the mean. Are there questions on those? Because those are a little bit of mind benders. Okay. If there are questions, you can stick around. I just wanted to finish this off by, that didn't clear. There it is. Showing you your homework. So, oh, I went too far. Okay, there it is, sorry. The only thing I wanted to add as far as your homework goes, for the AP documents, I didn't clarify this on Monday because I didn't really fully understand it on Monday. The 4-year plan is only for those who are currently in or interested in the AP Academy. And my understanding is that they want this filled out even if you did this last year. It's just maybe to keep you on track, make sure you're up to date. If you are not interested in the AP Academy, just skip that part. All right, but you do need to do the AP contract. The progress check, once you are signed up for AP Classroom, you should be able to go on your page, maybe in the top right, when you go into the statistics class, you should be able to see assessments, and you can find Unit 1, multiple choice questions, progress check A and B. And it's just to see where you're at. I'm not grading this for correctness. I'm going to give you points for completing it. Okay, if you have not finished Unit 2 homework from last week, make sure you get that done. And then besides that, here's your homework for tonight. And we're going to be looking at Chapter 9 tomorrow. So if you are good to go, I will see you then, and have a wonderful day.
Thanks, Mr. Davis.
Thank you,
Thank
Mr.
you.
Davis.
Good rest of your day.
Thanks, you too.